All right, so last time we started talking about aldehydes and ketones. We went over some ideas about little bit about how they're made in industry and which are some of the more common aldehydes and ketones, certainly the smaller ones. We discussed how to name them a little bit. Today we're going to get a little more specific about certainly the nature of the carbonyl group, what makes it special, what gives it its special reactivity and properties, and what we can expect to find when there's a compound that has a carbonyl group in it, especially aldehydes and ketones. We're going to cover other carbonyl-containing functional groups like esters, carboxylic acids, amides, all those guys in later chapters. But we're mainly going to be focusing on aldehydes and ketones in this chapter. And the main thing to understand about pretty much any carbonyl group is that it's quite a polarized functional group. And this doesn't just apply to aldehydes and ketones, but recall that the nature of the carbon-oxygen double bond is that it's highly polarized towards the oxygen atom. That's because oxygen is a good deal more electronegative than carbon. And so as a result, the oxygen is going to have a partial negative charge and the carbon a partial positive charge. And that's one way of looking at it. Another way of looking at this phenomenon is by resonance, because all carbonyl groups, again, regardless of whether they're in aldehydes or ketones or any other functional group, are resonance stabilized species, meaning that there's a minor contributor to the overall structure, minor but important, that has a minus charge on oxygen and a plus charge on carbon. So that means that the carbon atom is going to want to react with things that have a negative charge, like nucleophiles, as we're about to get to in a moment. And the oxygen wants to react with things that have a positive charge, most especially H+. And we're going to talk about that quite extensively today as well. So one result of all this is, as I said, that in aldehydes and ketones, and indeed other carbonyl compounds as well, they like to react with nucleophiles. So recall that a nucleophile is a Lewis base. It's a species that is extra electron density. I'm going to present this a little differently than in your book. I hope my way is a little bit clearer. But it means that in the presence of a solvent such as water, if you have I'm just going to use a generic nucleophile like this. We're going to say it's some species that has extra electron density. This nucleophile can be either neutral or negatively charged. And let's say, finally, of course, we have some carbonyl compound. The nucleophile is going to tend to react with the nucleophile. And this is how, let's see, this is in neutral or basic solution. Let's see, neutral or basic alkaline. Can I go SOL''N for solution? Is that all right? What we find is that the nucleophile will react with the carbonyl compound and give an intermediate that looks like this. So you can see how the nucleophile has, it's a strange word that we use, but we say the nucleophile has attacked the carbonyl carbon. It's a violent subject, organic chemistry. But the nucleophile has attacked the carbonyl carbon and in so doing, broken the carbon-oxygen pi bond so that we've gone from a double bond to a single bond. And then in a subsequent step, this intermediate can take a proton from water and make a neutral product that looks like this, and you would also get a hydroxide ion, OH-. So I thought I'd present it with the equation balanced. Your book also points out that these steps can sometimes be reversible, and that's true. Some nucleophiles can add reversibly to the carbonyl, meaning they can add and then fall back off again. We'll see some examples of that. Some nucleophiles can only react irreversibly. In other words, once they attack the carbonyl and form this kind of intermediate, they're not coming back off again. And we'll see some examples of nucleophiles of that type as well. Another important thing to be aware of when it comes to carbonyl groups is, of course, this carbon is sp2 hybridized. We'll be bringing that up again later. That means that it has the shape of an equilateral triangle with 120-degree bond angles. But after the nucleophile attacks, now that carbon is sp3 hybridized, and that remains sp3 hybridized in the product. So here, I didn't draw it using a tetrahedral shape. I just drew a flat structure. But of course, recall that in sp3 geometry, we have 109.5-degree bond angles and the shape of a regular tetrahedron about that carbon atom. So this is what occurs in neutral or basic solution. A similar thing happens in acidic solution, except the steps are reversed. In this case, if we have, let's say, a hydronium ion, which is the form acid will take when it's dissolved in water. Whenever you dissolve any strong acid in water, some, not all, but some of the water molecules will get converted to hydronium ions, H3O+. And then let's say we also had some nucleophile and our carbonyl compound as well. Oops. In this case, what will often happen, what will usually happen, and of course I should have put another plus sign over here, H2O plus this, you will have the carbonyl oxygen being protonated, which will put a plus charge on that oxygen. And so you'll still have your nucleophile and now a water molecule. Let me move this over here just for a moment. And so then your nucleophile can attack and you'll get the same type of product. Now the plus charge is gone from that oxygen. Our carbon atom has gone from sp2 hybridized to sp3 hybridized. And you again get this kind of addition product. So these are addition reactions. That's why they call it nucleophilic addition to the carbonyl group. And we'll go over some more information about that as well. That's technically in the next section of chapter 9. But these are addition reactions, and you can tell that because you start off with more species than you end with. Remember that an addition reaction in general is of the type A plus B yields AB, or A plus B plus C yields AB plus C, something like that. So they always involve two or more species coming together to make one bigger one. And certainly aldehydes and ketones like to undergo addition reactions. So one thing I should point out is when we protonate this oxygen atom to get an intermediate that looks like this makes the carbonyl carbon an even better electrophile or even better Lewis acid than we started with, because now the species has a full +1 charge, whereas before the total charge in the carbonyl was or on the species itself was 0. So that makes it even more want to be attacked by a nucleophile. So again, here we're just going over general basic ideas about the carbonyl groups that we find in aldehydes and ketones, and getting ready for some of the reactivity that we're going to encounter. I also want to point out that other things being equal, aldehydes are slightly more reactive than ketones. I'll even write it down. Or you could say ketones are slightly less reactive than aldehydes. And that's for a couple of reasons. One of the reasons you could call steric reasons, meaning simply having to do with how much room is there. If you compare a typical aldehyde to a typical ketone, well, of course, this hydrogen atom that you find on the aldehyde is going to be smaller than whatever alkyl group is on the ketone. That means that any nucleophile that wants to attack that carbonyl carbon has a much easier time of doing so. There's more room for it to attack the carbonyl carbon in an aldehyde than there is in a ketone. They're both pretty reactive towards nucleophiles, by the way, but you have to give the edge to aldehydes. They're slightly more reactive. And another reason that aldehydes are slightly more reactive than ketones is more of an electronic reason. Remember that this alkyl group, whatever it might be, is going to be larger than the hydrogen. And while the aldehyde has only one alkyl group, the ketone is two of them. And both alkyl groups come with their own extra electron density due to all of those carbon-carbon and carbon-hydrogen bonds that you find in the alkyl group. There's a lot more electron density in an alkyl group than there is in just a single hydrogen. So whereas indeed, again, the carbonyl oxygen pulling electron density away from the carbon, to some degree, these alkyl groups compensate by donating electron density towards that carbon. But the aldehyde is only one of those alkyl groups. The ketone has two of those alkyl groups to help donate electron density towards that carbon and stabilize it against nucleophilic addition. Again, both are still pretty reactive, but for both just reasons of there's more space around the aldehyde carbonyl than around the ketone carbonyl for a nucleophile to interact with and attack, and also because there's more electron density stabilizing the carbonyl carbon, stabilizing that partial plus charge in the carbonyl carbon in a ketone than you find in an aldehyde. Those, I would say, are the two main reasons that, other things being equal, again, as long as you're comparing oranges and oranges as much as you possibly can, so to speak, in that case, we find aldehydes are slightly more reactive towards nucleophiles than ketones are. Let me just make sure I'm not forgetting anything. Nope, so far so good. Oh, you know what I just realized? I just told you about the second page of my notes instead of the first page of my notes. So I'm going to go a little bit out of order. I'm going to blame the rain for this one, as opposed to early senility. Good, I think it will still work. Any questions so far then? And of course, some of these things I've mentioned already. We already mentioned how carbonyl carbons are sp2 hybridized, how the carbon-oxygen bond is highly polarized towards the oxygen. So we've already covered that. There's both an electronic reason for that and a resonance reason for that. Yes, I also wanted to point out, since we've already seen cases where this carbonyl oxygen can be protonated, I do want to point out that that kind of intermediate itself is also resonance stabilized. In other words, the protonated ketone or aldehyde also has another resonance form, just like it would without the proton being there. And that would look like this with the plus charge on carbon. So it's more stabilized this way. The oxygen and the carbon are effectively sharing that plus charge. So, but those are the two main things to remember, at least for now, about the carbonyl groups that you find in aldehydes and ketones. The carbon likes to react with nucleophiles, as we've said over here, and the oxygen atom is able to be protonated because it's got a partial minus charge. Again, you can look at that in either way. You can say it's got a partial minus charge by virtue of the oxygen being more electronegative than carbon, or you can also say the oxygen is a partial minus charge due to resonance. This is a minor contributor to the overall structure, but it's an important minor contributor. And as a result, we've got a partial negative charge in that oxygen. So no wonder it's possible to, to protonate that oxygen atom. And when you do, of course, the resulting species is still resonance stabilized. Main point I want to make here, main takeaway from all of this so far, I would say, is we need to understand that carbon-oxygen double bonds and carbon-carbon double bonds are very different critters. They have completely different reactivity. We learned in chapter 3 how carbon-carbon double bonds tend to react. We said that they tend to undergo addition reactions with electrophiles. And we looked at, I don't know, 4, 5, 6 reactions that alkenes undergo. But carbonyl groups don't tend to undergo reactions with electrophiles. They tend to be the electrophile. And they tend to undergo reactions with nucleophiles. Again, remember, an electrophile is a Lewis acid, and a nucleophile is a Lewis base. So C double bond C and C double bond O are completely different animals. They have very different reactivity. And again, there's going to be, 2 or 3 chapters, I would say at least, where we're going to go over the reactivity of the carbonyl group. It's kind of the main topic in the second semester of organic chemistry in your sort of standard 2-semester organic chemistry sequence. In fact, in my Chem 228 class right now, we're talking about carbonyl chemistry pretty extensively. And we'll do so also in here to some extent. The nature of that carbon-oxygen double bond also affects the properties of compounds with carbon-oxygen double bonds, certainly by way of polarity, as well as in other ways. And there's a comparison your book makes, which again, I would like to clarify a little bit. They're not wrong. I just think it needs a little bit of clarification. Your book is comparing hexane, there's hexane, with pentanal, which looks like this, with 1-pentanol, which looks like this. I'm even going to try to draw it so you can see the similarities between the molecules. And the reason it's making this comparison, which is the main thing I wish they'd explained a little more thoroughly, is all of these compounds have about the same molecular weight. So that means that any difference you see in their properties is not going to be because you're comparing apples and oranges, not because you're comparing molecules of different weights. Of course, you would expect something like boiling point to go up the bigger a molecule gets. But that's not the case here. This is a very reasonable comparison because, again, all of these molecules have more or less the same molecular weight. It's not identical, but it's pretty close. And then, as we've so often done here, your book is comparing the boiling points of these molecules. For hexane, it's 69 degrees C. Of course, I don't expect you to memorize these numbers. I don't have them memorized myself. For pentanal, it's 102 degrees C. And for 1-pentanol, I'm actually surprised pentanal is so close. It's 118 degrees C. And you can see that the boiling point is going up as we go from hexane to pentanal to 1-pentanol. I'll even write those out. Why should I be stingy? Hexane, pentanal. You don't need to say 1-pentanal because as soon as you put that al ending on it, implying it's an aldehyde, it's understood that carbon 1 has the carbonyl on it. If it didn't, it wouldn't be an aldehyde. It would be a ketone. So we just call it pentanal. Here, though, we have to say 1-pentanol because you have to say where the OH group is. 2-pentanol and 3-pentanol also exist, but this is 1-pentanol we're talking about here. So the reason for this is first of all because pentanal and 1-pentanol have polar bonds in them, right? We've already gone over how the carbon-oxygen double bond, as well as the carbon-oxygen single bond for that matter, is highly polarized towards the oxygen. And that's going to mean that dipole-dipole forces come into play. And these are attractive forces. You talked about these intermolecular forces in Gen Chem, but these are attractive forces that we need to overcome in order to separate individual molecules one from another. And in order to go from a liquid to a gas, isn't that exactly what we're asking the molecules to do, to separate from each other into larger distances? So in order to do that, we need to put in more energy in the form of heat for pentanal and 1-pentanol. And so that's reflected in the higher boiling points. And again, you don't have to memorize the boiling points. I would never do that to you guys. What is the boiling point of so-and-so? No way. I'm not interested in you memorizing a bunch of numbers just for the sake of memorizing numbers. But we see an additional effect going from pentanal to 1-pentanol. Hopefully you already see it. It's that in 1-pentanol, we've also got hydrogen bonding because we've got an oxygen-hydrogen bond. And so 1-pentanol is able to act both as a hydrogen bond donor and as a hydrogen bond acceptor. And so those are additional intermolecular forces that need to be disrupted in order to get the 1-pentanol from the liquid state into the gaseous state. So no wonder the boiling point is even higher. Though I have to admit, I wouldn't have expected pentanal to have such a high boiling point. If you had asked me to guess, I would have guessed something like 85 or 90. So I'm surprised it's that close to pentanol. That could be to some degree because pentanal is able to act as a hydrogen bond acceptor, which the book does point out. But I thought that just needed, I don't want to be that guy that reads your textbook to you, but sometimes I find your textbook has good examples, but I kind of wish they explained it a little bit better. So that's when I take the liberty of using the same examples that are in your textbook. So other than that, we've already gone over a considerable amount of information in section 9.6. It's already laid out for you here, but just to go over that again, we've talked about how, I'll go over it only very briefly, but we talked about the nature of the addition reaction to the carbonyl groups in aldehydes and ketones. And again, here I'm being just very general and not getting into specific compounds. We'll get into some specific examples, of course, as well. But what we're saying is that when the aldehyde or ketone is in neutral to alkaline solution, I would say, it can tend to undergo addition reactions with nucleophiles, such that the nucleophile will at first attack or add to that carbonyl carbon. And you can see how we've gone from C double bond O to C single bond O. So we've broken the carbon-oxygen pi bond. And as a result, we now have a minus charge in oxygen. If I were going to draw a mechanism for this, which is not something I want to emphasize really heavily, but it's not that hard, you would show the nucleophile donating its electron pair towards the carbonyl carbon. Remember, arrows always start where the electron pair starts and end where the electron pair ends. And then you would show the carbon-oxygen bond, pi bond breaking. You could draw this arrow on either side, of course. They're equivalent ways of showing the same thing. And so you can see that we've gone from 2 lone pairs to 3 lone pairs around that oxygen with a minus charge. So that's how you would show that. And once we have this intermediate with the minus charge, again, this is what you would find in, I would say, neutral to alkaline solution. Then this species can abstract a proton from water in order to give you hydroxide ion and the final addition product. I can even show you what that mechanism looks like. It's again not complicated, but I have to draw out the water molecule so as to be very clear where the electrons are. But here we have this oxygen effectively picking up H+ from water, and we break the oxygen-hydrogen bond. We put those electrons onto, I should have drawn my lone pairs here too. That would look a little better. We put those, the electrons in the oxygen-hydrogen bond onto the oxygen atom, and that's where your OH- comes from. So like I said, I don't want to emphasize mechanism very heavily in this class, but occasionally when it's relatively simple, like over here, it's not such a huge problem. In acidic solution, the same thing happens, but the steps are reversed. And that's because in acidic solution, we need to make the carbonyl compound a little bit more electrophilic yet before it will react with the nucleophile. That's because in acidic solution, you don't want to have any species with O- like this. That doesn't make sense in acidic solution. It's too strongly basic. So you're not going to be able to generate a species like that. So that's why you need to protonate the oxygen first. And we can show that as well, but the mechanism is going to look very much the same, except the order of the steps is reversed. We've got a lone pair taking a proton off of the hydronium ion. Here's your H3O+, and that would look something like that. That puts the proton onto the oxygen. And then, of course, once again, your nucleophile will attack the carbonyl carbon. We break the carbon-oxygen pi bond, and we put the electrons onto the oxygen. That gets rid of the plus charge. And you get your addition product that looks like this. So these are just some basic concepts that lie behind nucleophilic addition to carbonyl groups. And I think with that, we're all caught up. Good. So sorry about the little mix up here. I also want to talk about hydration of aldehydes and ketones. I don't want to get hardcore into actual like synthetically useful addition reactions to aldehydes and ketones just yet. I'll save that for Monday after we come back from our exam. And then, as I said, if we have time after this, I'll see if we can't do a little bit of exam review. Good. Any questions so far then? I know you're just dying to get back out there into the rain, though the professor before me said it was worse before. It was going like sideways. At least it wasn't like that when I was walking over here. Actually, one other quick thing. I know I'm getting off topic, but I thought that you weren't supposed to complain about rain in this part of Texas. I've been scolded by perfect strangers, like standing in line at the store, for complaining about rain. What are you doing? We need the rain. You know, that type of thing. So, okay, I won't complain about the rain then. Growing up in New Jersey, you always complained about rain. Anyway, back to the subject matter at hand. Good. So one example of this type of nucleophilic addition to aldehydes and ketones can occur in either acidic or basic solution. And that is the hydration or addition of water to aldehydes and ketones. And I just realized I took great pains to say how C double bond O and C double bond C are different critters. It is interesting that you can also hydrate carbon-carbon double bonds, but they're very different types of reactions. They're almost the reverse of each other. They're sort of opposite concepts to each other. The way the hydration works of aldehydes and ketones is a very different kind of reaction, even though both involve the addition of water. That just now occurred to me. But this is something that can occur in either acidic or basic solution. So again, speaking at first very generally, these steps are usually reversible. This can occur in basic solution. Here showing just a very generalized aldehyde or ketone reacting with water. That's one possibility. Or this will also happen in acidic solution. I'm sorry, did I miss a question over there? I do tend to be kind of blind about, especially when half the class is behind my head. Okay, so this can also occur in acidic solution. So I'm here showing H3O+. You could also write H2O, comma, H+, same thing. H3O+ means dilute aqueous acid. One of the things that I'll just give as an aside is whenever you see H3O+ mentioned, it implies that water is also present. That's actually something that OWL does that I'm not a huge fan of. sometimes OWL will write H3O plus comma H2O. And I don't like that, it's redundant. You can't have H3O plus without H2O. In fact, H3O plus means not that you have only H3O plus ions, it means you have some H3O plus ions dissolved in water. So I just thought I'd give you that as kind of an aside. If you ever see H3O plus or H2O H plus, you can write it either way. But whichever way you write it, it implies that water is also present. In any case, the products will be the same. You get what's known as the hydrate of the aldehyde or ketone. Now, I have to be honest with you guys and say this is not a synthetically useful reaction. In fact, quite the opposite. Normally, this is a reaction that in any organic synthesis related industry, we take great pains to avoid, because once you form this hydrate, this stuff is now dead effectively. It can't undergo any further addition reactions. So even though the process is reversible for most aldehydes and ketones, we want to keep the concentration of this hydrate as low as possible, since there's going to be some water vapor naturally present in air, maybe especially today. But in all seriousness, this is normally something we try to prevent from happening. We like keeping aldehydes and ketones over drying agent, so that if any residual water gets in from the air, it gets immediately soaked up by the drying agent as opposed to making some of this hydrate. So this is not a synthetically useful reaction. This is not something they would use, again, with maybe one interesting exception that I actually learned from your textbook. But in general, this is not something synthetically useful. In general, this is something we actually try to avoid. But this reaction is illustrative of other nucleophilic addition reactions to aldehydes and ketones, which, like I said, we're largely going to talk about starting on Monday. But just to give some examples of this, if you took acetone, which as a recall is the smallest possible ketone, and you treat this with water with a catalytic amount of hydroxide, well, you will get, to some degree anyway, it's an equilibrium, but to some degree, the hydrate of acetone, which would look like this. And again, a reminder I should have said from the beginning, remember that we go, in all these cases, we go from an sp2 hybridized carbon to an sp3 hybridized carbon. We go from 120-degree bond angles in trigonal planar geometry to 109.5-degree bond angles and tetrahedral geometry. So that's one possibility. Another one, this is the one I learned from your textbook that I thought was kind of interesting. If you take trichloroacidaldehyde, you can treat this with either base or acid. And actually, in this case, the equilibrium heavily favors the product. Not that I really care if you memorize this, but you can use either base or acid, doesn't really matter which, and you will wind up getting what's a species known as chloralhydrate. I'll start writing out some of these names as well. So this is trichloroacidaldehyde. This guy is chloralhydrate. Not that I really care that you memorize the name, but it has a name. And chloralhydrate is important because it was used for a while in humans as a sedative and an anesthetic, and I guess it's still used that way in animals, which really comes as a surprise to me. I didn't know this. I'd heard of chloralhydrate, but I didn't know its structure was this simple. And I didn't know it came from trichloroacidaldehyde, which I would have expected to be pretty toxic, by the way. So maybe it is still a little bit toxic. Maybe that's why they don't. Maybe I think they said it was used in horses, and maybe they being such large animals, they can tolerate a certain amount of it. But I don't think chloralhydrate is used any longer in humans unless you go and get a Mickey Finn, which I wouldn't recommend. This compound, of course, is acetone. I don't know that its hydrate really has a name. It's the hydrate of acetone. But to give another example, if we took cyclohexanone, and again, you can use either base or acid, it will undergo addition of water. You'll get a compound that looks like this. So this is cyclohexanone. And its hydrate would look like this. And you can see, by the way, in all three cases, we have literally added H2O. If you compare the formula of the starting material and of the product, you'll find there's an additional 2 hydrogens and 1 oxygen in the product than in the starting material. Hence, hydration, addition of water. So, like I said, this is not the sort of reaction that will get used synthetically to any great extent. Normally, this is something we actually try to avoid happening. But it is illustrative of addition reactions to aldehydes and ketones, like formation of hemiacetals and acetals, which is what we're going to start with on Monday. So, so for that reason, I do like introducing the topic of addition to aldehydes and ketones with hydration, even though it's not exactly synthetically useful. Good. And with that, I think we're caught up with the syllabus and we've covered all the material we really need to today. I'm sure there's some interest in my doing some exam review, so I'll do what I can in the remaining 11 minutes. We already went through chapter 13. I believe we're also doing 15, 18, and 7. We did just cover chapter 7 fairly recently, but let's see. So chapter 15 is lipids and chapter 18 is nucleic acids. Mainly, again, what I would say to focus on for both 15 and 18 is structure. I'm mainly interested in you guys getting a background in the structure of nucleic acids and the structure of lipids, not asking you to memorize particular compounds. I don't expect you to memorize the nucleotide bases, for instance, or I wouldn't say which of the following is oleic acid coming from the chapter on lipids. I don't care if you memorize particular fatty acids, but I do expect you to know what fatty acids are and that they're long-chain carboxylic acids. So that's the sort of thing I'm looking for, but not memorizing scads and scads of molecules. I don't think that's a good use of your time. One thing I'm hoping that you remember from the chapter on nucleic acids, and really the main thing I think we covered, is in general what their structure is like. And we said that a typical nucleotide, or would have, and again, I don't have the nitrogen bases memorized, but it would have your, I don't know why I'm drawing it so small. It's not like there isn't room. But it would have your ribose sugar. Ribose is a 5-carbon sugar, and I'll put R here because that's going to be what determines whether it's a DNA type nucleotide or RNA type. And over here is going to be your nitrogen base, whichever it might be. In DNA, that would be, let's see, adenine, guanine, cytosine, or thymine. And in RNA, that would be adenine, guanine, cytosine, or uracil. But like I said, you don't have to memorize the nitrogen bases. If you need those structures, I will give them to you. But the nitrogen base attaches as what's known an NO acetal, meaning it's got a carbon-nitrogen single bond and a carbon-oxygen single bond on the same carbon. At the 1' carbon, the 2' carbon is going to be the one that determines whether you're looking at RNA or DNA. I'm leaving this just as an oxygen at the moment. We'll fill in more later. The 3' carbon is there, 4' over here, and 5' is the CH2 group. So if we're making a polynucleotide, like a dinucleotide, then you're going to have a phosphate ester attaching the 3' carbon of one sugar to the 5' carbon of the next one. And the rest of the structure will be very much the same. This is the 1' carbon. Here's my hydrogen. This again is going to be your nitrogen base, whatever it might be. And I'm going to put H and R over here. And H, this could be OH, or it could have a phosphate ester here. And this is the 2' carbon. This is the 3' carbon, 4', and 5'. And then just a reminder, in the case where R equals H, you're looking at a DNA type nucleotide. And in the case where R is OH at the 2' carbon there, you're looking at an RNA type nucleotide. And I don't say that's a full and exhaustive description of every last thing you need to know from chapter 18, or is it 15? I think it's 18. Yep, 18. I don't say that's every last thing you need to know, but I think that's what we mainly focused on, is how to draw the structures of these things. In chapter 15, which was on lipids, we discussed the structures of several different fat-soluble compounds. And I'm, again, not expecting you to memorize particular ones. I would never say which of the following is testosterone or which of the following is prostaglandin F2 alpha. I don't expect you to memorize them, but I would expect you to be able to recognize a prostaglandin or recognize a steroid hormone, for example, or recognize a triglyceride or understand what are the components of a triglyceride or of a phosphatidate or all of these other ones that we discussed. The chapter, I would say, revolved around fatty acids, which again, mainly are going to look like this. They're just going to have really long alkyl chains if they're a saturated fatty acid. In the case where you would have an unsaturated fatty acid, then you would have at least one cis double bond in the molecule. And again, that is something peculiar about unsaturated fatty acids. The ones that occur naturally are have cis double bonds, which is weird because cis double bonds are less stable than trans double bonds. Nonetheless, that's true. The so-called trans fats do not occur naturally. And those are the ones that are bad actors. They cause wear and tear on your metabolism because we, I think they even call it oxidative wear, which is, by my understanding, I'm no biochemist, but my understanding is it means it generates a lot of free radicals. And you know, free radicals are bad guys. They're getting into your DNA and causing mutations. It's bad. So as opposed to the ones with the cis double bonds, we have well-established and constantly running metabolic pathways to handle breaking those down. So, but fatty acids look like that. They're just essentially long chain carboxylic acids. We were just writing RCO2H for fatty acids, right? Where R is just something really, really big. And that was one of the main types of lipids we talked about. There were a lot of other types of lipids that I actually gave the structures of some examples in the class notes. And also went over in the class notes what are the main things to focus on in terms of structure. I guess if I were to go over one more example of a lipid that involves these fatty acids, it would be triglycerides. You will get your, if you go to the doctor for a checkup and get your blood drawn, you, among many other things, you will get your blood tested for triglyceride levels. And triglycerides are a triester of glycerol, which is 1,2,3 propane triol. Whoops, I don't want OH there, do I? With 3 fatty acid molecules. So a typical triglyceride would look something like this. But it will contain ester functional groups, as will waxes. Waxes also contain ester functional groups. So In this case, of course, these three R groups can be either the same or different. Both are allowed. But when you get your blood tested for your triglyceride levels, it's looking for these. And these are this is the way, at least by my understanding, again, I don't consider myself particularly strong in biochemistry, but my understanding is this is the main way that fats are stored and transported in living systems. And certainly we have enzymes that can cleave these ester bonds and give us glycerol and the individual fatty acid molecules back. Glycerol is something our bodies know what to do with. It's easily converted into dihydroxyacetone, which is something that's a dihydroxyacetone phosphate is a common metabolic intermediate that your body knows exactly what to do with, and same in other living systems. We also talked about how triglycerides can be used to make soaps. And we talked about two different kinds of soaps. We talked about sort of the old school kind of soaps that you make just by heating, let's say, Crisco in sodium hydroxide or potassium hydroxide, and you can get soaps that way. And we also talked about synthetic detergents. And we talked about how we talked about both of those, how they're made. So we went over in some detail what the procedure is, what the reactions are that are involved, and that's another thing that we covered in class. And even though I still have 2 minutes, I can't really think of anything else. Most of the rest of chapter 15, in terms of the structures, I already put in your class notes. And again, chapter 7, we just covered recently. Plus, there's a study guide on it. So I'm no more eager than you are to get out into the rain, but there's only 1 minute left, so I think that's a good place for us to end. So with that, I will see you all on Friday.